Okay, so after talking to some of you about the quiz, some of the feedback I got included observations that not all of you feel super comfortable writing programs in Racket and Haskell independent of implementing programming language concepts. A bunch of you said like the thing that we want is to just write some programs in these languages. So I thought maybe a good way to do this would be to work through an example with all of you. So just like the previous mini videos, let's do the thing where you're all typing in the program with me. So if you want to pause to type stuff in, that's great. But I think you will get more out of this if you're typing along with me. So by the end of this video, what we'll have is a program that will print out a 2D image that we will define in terms of a data definition. That in particular will print out this logo here. We'll say it's the logo for this iteration of the class. Okay. So I think we all know what a binary tree is, right? It's a tree that either holds a leaf node with some value, or it's an intermediary node with two children. We're going to implement something called a quad tree. The difference between a binary tree and a quad tree, as you might guess, is that a quad tree will have 4 parents and not 2. So let's write this first in Haskell. So data quad tree defines a data type called quad tree. And because this is a tree, it's a recursively defined data type. This is going to be a sum type where either we have our base case or our recursive case, right? So the base case, it's going to be a leaf. For the moment, let's say it holds integers. Otherwise, it's going to be a node containing a quad tree, quad tree, quad tree, quad tree. And I'm going to add one more thing here. This just lets it be possible to print this out in the interpreter. Okay, now let's write a function that operates on a quad tree. The simplest one I can imagine is one that just returns the height of a quad tree. So we say height is defined as a quad tree, and it will produce an int. So we know that there are 2 cases that we have to handle here, right? Because a quad tree can be one of 2 things, right? So what do we do if the height is a leaf containing some value? Well, let's say the height of just one leaf is, let's say it's 1. It's not like an empty list, so maybe you could argue it's 0, but we can call it 1. Notice that we don't need the identifier that we bound there, right? So just to remind everyone what this means, leaf is like a constructor that takes one argument, which is an int, and node is like a constructor that takes 4 parameters, all of which are subtrees. We don't use that field, so we can just underbar it to indicate that it doesn't matter. Another thing we can write is height of a node. We should give each of these names. Quad trees are nice because they let you divide up a 2-dimensional grid into 4 subgrids. So let's call it top left, top right, bottom left, bottom right. And this will be the obvious thing, right? It'll be 1 plus max of the max of height top left, height top right, max height bottom left, height bottom right. Okay, so let's open up the Haskell interpreter. And I'm going to load the file that I wrote with :L. And now we can start calling height with a bunch of quad trees, right? So what is the height of the quad tree that's just a leaf? Okay, as expected, it's 42. What about height containing the node leaf 1, leaf 2, leaf 3, leaf 4? We get 2, right? And so because this is defined recursively up here, we could come up with fancier quad trees, and then it would recurse appropriately using the structural recursion that we've seen in this class. Just to drive home that leaf and node are really constructors, let me show you an implementation of Quadtree that I did in Java. right? So Quadtree is an abstract class that has two subclasses here. One is the node, whose constructor takes 4 quadtrees. The other is a quad leaf, whose constructor takes a value. The thing to notice is that these are actually doing the same thing, right? So the inheritance tree in Java is saying that a quad tree will either be a node or a leaf. And we do the same thing with the sum type in Java. Sorry, with the sum type in Haskell. Now, something I'd like to point out about my implementation in Java is that Quadtree actually takes a type argument here, right? So I use generics in Java to specify that this Quadtree here would take an integer for its leaves. So down here, what we can see is our implementation of quad leaf holds a private field called val whose type is t. So it's specified as part of the type up here, right? So I could also write something like Quadtree string something like that. And this would ensure that all leaves that were passed to quad nodes have the same type within them. We can do the same thing in Haskell by implementing something called a type parameter. So here what I've done is I've changed the data definition for Quadtree to consume a parameter a, and we'll say that leaf is not the type int, but rather an a. So when we make the initial changes here, we see that this is now a data definition for what we say a polymorphic quadtree, whose type can be specified when instances of the tree are constructed. Okay, let's open up the Haskell interpreter. Before we load this file, what I need to do is I also need to change the data definition of height to consume a quadtree of any type A. Because what we do, we don't actually ever do anything with the value, so we can leave this A unspecified here. So let me load quadtree.hs, right? And I can say, I don't know, leaf 42. And what is the type of leaf 42? It's a quadtree of some type A, where A is a number. So you can think of this thing here as it basically implements the number interface. Right, so I can say leaf 2/3 and it should say fraction. I can say leaf hello, and it says it's a list of characters, so it's like C, it's like a char star. So this lets us create quadtrees of different types just by providing a type variable in our data definition. Let's create another data definition. So because I mentioned that quadtrees are nice for 2D things, let's define a pixel. We'll say that a pixel is either going to be black or white. So something that's interesting about this data definition here is that this is a finite type. Right? We can have infinitely many implementations of a quadtree because of the recursive nature, quadtree can be arbitrarily nested. Whereas with pixel, according to this data definition, there are only ever two instances of a pixel in the world, right? It's either black or white. It's like an enumeration in C, or even like a Boolean true or false, right? Like you can think of true and false as being constants. You can think of black and white because they take no parameters. You can think of them as being singletons as well. So unsurprisingly, something we can do with quadtrees, now that we've defined a pixel, is we can create instances of quadtrees with pixels, right? So I can write, give me the type of a leaf containing the black pixel, and we can see that it is indeed a quadtree containing elements that are pixels. We can probably do something a little bit fancier too, right? I can also say, give me a node with a leaf of black, leaf of white, leaf of white, leaf of black, we see that it is also a quad tree whose types are pixels. Let's write a function that operates on a pixel. In particular, I'm going to invert, we'll say that invert pixel takes a pixel and produces basically the opposite, right? So if this was a Boolean, it'd be like not. So we'll take pixel and we'll say pixel, invert pixel. When we give it black, this should produce white, and invert pixel of white should give us black. So when I load this in the interpreter, I can say invert pixel black gives me, one thing we should do up here is deriving show. Right, so if you see this error ever, no instance arising from use of print, you want to make sure you derive the show type class in order to be able to print stuff out. So let's load that one more time. We see white, pass in white, we get black. Great. So now let's write a function that inverts all the pixels in an image that's defined in terms of a quad tree. Right? So we'll say invert image will be a function that takes a quad tree of, is it quad tree of any type? No, it has to be a quad tree that is in particular of a pixel and produces a quad tree of pixels once again. Right? So let's write invert image. Remember, we have two cases here, leaf node case and the node case. So we'll do leaf pixel. This is now becoming leaf of invert pixel pixel, and invert image node top left, top right, bottom left, bottom right is going to be the node where we invert the image of the top left, invert the image of the top right, invert the image of the bottom left, and invert the image of the bottom right. Okay, let's open up the interpreter and load our file. So let's see about inverting some images. So we'll invert image leaf white, and we should see leaf black. And if we do the opposite, and what about a non-trivial case here? So node leaf black, leaf black, leaf black, leaf black. You see that all the subtrees are inverted just like we expected it to. Now you might say, Nathan, this was a lot of work. I bet I could have written invert image without invert pixel, right? Like something we could have written would be invert image if the leaf is black. This simply produces leaf white, and vice versa. Generally, I suggest that when people start operating on a different piece of data, right? So when we were writing invert image, we were operating on quad trees. And then when it became time to operate on the pixels inside the quad tree, I generally recommend that people start writing a helper function at that point. The idea is that because a pixel is a different kind of data than a quad tree, even though we glue them together when we have quad trees of pixels, splitting things up into helper functions kind of at the type level, in my experience, makes the code a little bit cleaner. Like you can focus entirely on dealing with implementing stuff that works on a pixel versus something that works on the quad tree, and it's easier to keep straight, at least in my head. So my recommendation is, instead of writing things like this, where you have one slightly more complicated function, I recommend the approach over here, where you defer operations on the pixel to a helper function, in this case, invert pixel. Now some of you may be thinking that invert image is crying out to be implemented as a higher order function. So let's write something called quad tree map. or let's do Qt map, which is a function that takes a function that goes from A to a B and a quad tree of type A and produces a quad tree of type B. So in this case here, let's write Qt map, where we're passed a leaf with some value. And how do we get a quad tree of B? Oh, actually, we need a function here, don't we? So how do we get a quad tree B out of a quad tree of A? Well, we're going to produce the leaf whose value is f of val. And we'll do the same thing with node top left, top right, bottom left, bottom right. And here we will produce node Qt map ftl, Qt map f top right, Qt map f bottom left, Qt map bottom right. So in this case, how do we implement invert image? Well, in this case, invert image will be simply Qt map invert pixel, right? And if we didn't want to curry it, I could do something like, I could write something like this. But because it's nice to have things curried, you write it like so. Just to clean things up a little bit here, I wrote an arrow here that should be equals. T in Quadtree needs to be capitalized, and then I need to pass in F to BR. So if I load Quadtree here, if we do invert image, leaf black, get leaf white. If I do node leaf black, leaf white, leaf black, leaf white, we get, given if I passed in black, white, I got white, black, black. So here we used a higher order function and an implementation of something that looks a lot like map in order to implement invert image without needing to specify the structural recursion ourselves. Towards the end of the class, when we start talking about things called functors, we will see that Quadtree can be implemented in such a way that it fulfills the definition of a functor. And indeed, anything that you can map over is, as we'll learn, what a functor is. Okay, let's move into Racket now, and let's start by writing sort of an equivalent definition for a quad tree of pixel. Right? So what I'm going to do is I'm going to do it a little bit differently, just to mix things up a little bit. We'll say that a quad tree representing a black and white image is either the symbol white, and this represents the entire sub image is all white. We'll do the same thing for the symbol black. The entire sub image is all black. Otherwise, it's quad node top left, top right, bottom left, bottom right, where TL, TR, bottom left, bottom right, are all quad trees. So let's do struct quad tree, top left, top right, bottom left, bottom right. Right, so this is our structure definition for a quad tree. Let's write some examples of quad trees in Racket. Define, there's an image of a snowstorm. So in this image represented by a quad tree, every pixel is going to be white. Let's do define power outage at midnight will be entirely black. Let's define a checkerboard to be quad node black, white, white, black. And then We can even make it a more refined checkerboard by define cboard2 will be a quad node containing cboard, and cboard. Let's proceed, now that we have this data definition, by writing a template that operates on a quad tree. Right? So we'll write define, I'll use it with match, quad tree op template quad tree. We'll fill it in here. Right? So when we start thinking about writing functions that operate on a new data type that we've never seen before, it's always good to think about things in terms of writing a template. Right? So this is going to be the basis for all structural recursion on a particular kind of data. And how do we get the template? Well, we followed the data definition exactly up here, right? So in this data definition, we sort of have three cases: the entirely white case, the entirely black case, or the combination here. And one thing I should say about the quad node here is that TL, TR, BL, BR divide the image equally into 4 quadrants. Right now, we'll just assume that it divides them all equally, so you get 4 evenly spaced images if you define a quad tree image instead of a quad node. Okay, so going back to the template, we know that we have to handle the case where we have white, so we'll do something. Similarly, if it's black, we'll do something. Another possibility is quad node, top left, top right, bottom left, bottom right. So we'll do something with, because these are all quad trees, we know that the recursion for the template is going to go back to them. So we'll do quad tree op template on TL. And the same thing for the other 3. Let me just copy and paste that. And change them like so, top right, bottom left, bottom right. So we will use this as the basis for all the functions that we write that operate on quad trees. So that sounds important, so I'll put a box around it. So I just realized a typo. Struct quad node. So if you caught that, good for you. Let's spend a little bit of time talking about how to draw images in Dr. Racket. And the cool thing about Dr. Racket is that it integrates really nicely with images. So in order to do this, I imported the pict module from Racket. So let's write some expressions. Here's a rectangle. That's 30 pixels by 30 pixels. I can fill that in with filled rectangle 3050. There's an optional parameter, color red, let's say. So that's nice. Now what can I do with images? Well, I can compose images together. I can put them side by side horizontally or side by side vertically. So we do horizontal with HC append rectangle 5050, and let's do filled rectangle 5050. So that puts a white rectangle next to a black rectangle, and we can do the same thing horizontally. Or sorry, now that we've done the same thing horizontally, let's do it vertically, like so. So this gives you a sense, given our data definition of a quad tree, how we might transform a quad tree into an image in Racket. So let's write a function that does that. Okay, let's write a function that takes a quad tree and an int. So this will be the size of the image and produces a picture. So let's call it define match quad tree draw, which takes a quad tree and the size. So what did we put here? Well, what we put there basically comes from our template. I'm going to copy and paste that wholesale down there. Let me fix up the recursion, right? So we want the recursion to be like so. So if I pass Quadtree draw a white with a certain size, what do I want to produce, right? Well, I want to produce a rectangle. Rectangle of size. What about black? Well, that'll be a filled rectangle of size and size. Now, what about the recursive case here? Well, in order to do that, I'm actually going to write it like a let expression. So I'm going to do let the new size, and I'll show you why I write that in a second. It's going to be half the current size. I'm going to do top row, which will be the horizontal concatenation of top left and top right. So that will be HC append Quadtree draw top left and top right. And we need to pass in a second argument there, which will be new size. So the intuition here is that in order to draw a Quadtree image of size 100, say, we've got it broken up into 4 different parts. And so each of those individual parts will be 50 by 50. And when we put them all together, we'll have an image that's 100 by 100, for instance. So that's why we divide size by 2 to get new size. Let me close that up there. And we'll do bottom row. I'll call it T row, actually. T row, B row. And let me just, if I give it a name like that, then everything kind of combines nicely. Bottom left, bottom right. So, what do I do once I've got T row and B row? Well, I want to put them on top of each other. So that will be VC append T row, B row. Let me make sure that compiles. Oh, right. Let's just do... So it's complaining because the find match expects me to match both the QT and the size. Let's just do this. So we'll only match QT. Oh, and then the syntax I think is slightly different. Okay, let's draw some images. So we had our examples up here. So let's do, I've already forgotten what we called this, Quadtree draw snowstorm. Let's say make it 100 pixels by 100 pixels. Okay, so we get a white image. Let's do the same thing with power outage at midnight. Ooh, very spooky. Well, what about the checkerboard? The checkerboard now is interesting, right? Because when we did the structural recursion on the quad node, we had to draw black, 50 by 50, and then white, 50 by 50, and then white and black again, 50 by 50, and then we glued them together using HC append and VC append. And just to close the loop on this, let's do cboard 2. We can see that now we had to go 2 levels deep in order to draw this. And indeed, if I make this a little bit bigger, we can see that this image here, power outage at midnight, is the top left of the checkerboard. And the checkerboard is the top left of checkerboard 2. Okay, now that we have a way to draw Quadtree images, let's write another another function. So let's do quadtree invert again. So we'll do define, yeah, so we'll use the template again. So we'll use define match the template. Quadtree invert. So what do we want to do when we're passed an image that's all white? Well, we want to produce black. And similarly with white. And otherwise, we just construct a new quad node, yes. We construct a new quad node with all of these sub-images inverted. So if we quadtree draw seaboard to 100, of course we get this image. But what happens if we quadtree invert the checkerboard and then pass that to quadtree draw? As we expect, everything is flipped. So I pasted in a more interesting expression here. This is a logo that spells out CSC324 that I spent a couple of minutes coming up with. So if I draw quadtree draw logo, let's make it reasonably big. Let's say 300. Something that's actually kind of nice about this is that you can see how the recursive structure actually comes into play when we draw the image. So if I just scroll to the very bottom of this expression, so this is what's being drawn here. And remember that this is top left, top right, bottom left, and bottom right. Notice that the top right of the final image is entirely white because I wanted the CSC to be sort of diagonal like this and 324 at the bottom like so. So there was nothing in the top right quadrant of the image, which means that I only needed one piece of data to represent that whole thing. So you can imagine why quadtrees might be useful if you have lots of sparse data in your image, because instead of having the pixel 1, pixel 2, pixel 3, pixel 4, and so on are all white, you could just say this subregion of the whole image is white, and it could be more memory efficient. So the last function I want to write today is going to be a function that simplifies redundancies in a quadtree. So notice I have an expression here. It's a quad node where all 4 quadrants are black. Notice that's the same thing as if we had just drawn black altogether. So let's write the function quadtree dedupe, which will take a quadtree and produce something. Let me write a signature here. This takes a quadtree and produces a quadtree. Let's go up to my template. Actually, I'll make the window a little bit bigger. Do that. Okay. So, how do we deduplicate something that's already entirely white? Well, we don't. We just produce white itself. Same with black. Now, you might say, for instance, here, if you wanted to say, do something like, you might write, if equal TL TR, and equal TR T, BL, and so on like that. That might be how you might write it before thinking of things in terms of pattern matching. But notice that we can do something here, right? So I'm going to leave this final arbitrary expression just for the time being. I'm going to write, and this kind of just follows straight from the informal definition of what quadtree dedupe should do. Well, if I see a quad node that's all black, What's the thing I want to produce? I just want it to produce black. And it would help if I wrote everything correctly. And we do the same thing with white. So this is really the meat of what Quadtree dedupe does. And it shows the power of pattern matching in these sorts of languages, right? Where we said we didn't need to manually say, is the bottom left equal to the top right and all these sorts of things. We were able to just express the structure that we want to deal with in this particular arm of a match. And then on the right-hand side, we can just say what do we expect it to produce. So let's deal with the general case right now, which will be, we're going to produce a quad node. Let's get the recursion right, like that. Let's run it to see if it, because those should be in parens. Like that. All right, so when I run Quadtree dedupe, quad node, black, 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 we should just get back black. And if we gave it a more complicated thing, like C here, for instance, then we just do structural recursion on quad node. So thanks for sticking around. I will leave you with something to do on your own time. It's to implement something called Quadtree overlay. So Quadtree overlay will take two quadtrees. So for instance, a C board, actually lowercase c board, and another quadtree, let's say white. And let me show you what Quadtree overlay should do. So if I do Quadtree draw C board with white, let's make it big, 300. You'll see what this does is this just passes through the image without having done anything to it. Now, if I pass it black, notice that the whole image then becomes black. So what overlay does is, if a subregion is white, it lets through the other image, and if it's black, the whole subregion becomes black. So to show you, let's remind ourselves what C board looks like, and let's do Quadtree draw C board 2, 300. So if we do the overlay of C board and C board 2, what we should see is this. Because the regions of C board and C board 2, where both of them are clear, is this region there, that region there. It's basically the diagonal, right? Like all other points are black regions in at least one of them. So if you have any questions, send me an email, show me your solution, it'll be interesting to see. If you come up with fun equivalents of logo drawn using Quadtrees, send them along. And hopefully this was insightful. If not, I mean, if it was and if it wasn't, let me know. So if it wasn't insightful, I won't keep doing them. Okay, thanks a lot.